Hi everyone, my name is Sahiba and I am from Michigan and I worked on a kind of computer science, a little bit data science type project. So I work with Princess Elodie, who is a grad student or a PhD student at CMU. Um, and my project was on using like machine learning models and just like learning about AI to predict the prevalence rates, which is basically how common COVID-19 is in a population. And I also analyze like demographic data, like the sex, the age group, and things like that. So some background, this was actually not my original topic. For the first like 1 or 2 weeks of Talaria, I was on like the background research stage. So I read this book with my mentor. It was a chapter 11 of like a book on pandemics. And we were discussing the idea that I suggested was pool testing, which was based off of like an independent thing I had tried for a school project, and I wanted to just expand on it in Talaria. And pool testing is basically putting into groups, as you can see here in this picture, is when you have like, let's say, for example, 5 people and all their samples go into one group. And then if that group comes up positive, then you know that someone in there is positive, but you don't know who. And if it's negative, then everyone's negative. So sometimes, like in certain scenarios, it can actually speed up COVID testing and save a lot of resources if you do like an optimal strategy. So that's kind of what I wanted to do originally was make like some kind of like algorithm that optimizes that. And we were reading on like the formulas and trying to derive them. However, the goal with that was the problem with that was that pool testing only worked with what's called a PCR test, which is not like it's not the regular rapid test. And so there wasn't really data that we were able to find to support that very much. And then also, the thing with, as you can see, this formula up here is just an example, but a lot of stuff with pool testing, the formulas given in the book we read relied on what's called false negative and false positive rates, and we didn't really know how to find those. And we were sure that there's a way maybe to explore that, but we decided in the time we have, we moved on to make a research plan to basically try to like do a data science type project where we used a bunch of data sets and combined them and cleaned them, and then we trained a machine learning model on like these um data sets to try to predict how common COVID would be. And so the implications with that would be like if someone was to actually use this model, they could like put in, for example, a month, like choose a month or choose a week of the data set and predict like how common is COVID, so they can see like how safe it is and things like that. And then I learned about principal component analysis, which is a technique to explore relationships between data. And that was to see the demographic data. So the first step was the data science lifecycle, which my mentor kind of talked me through. And it was something I had never heard of. Like I had not known the difference between data science and like computer science. So it was interesting that a lot of data science was it was a lot of the cleaning of the data because there was a lot of null values. So it started out, we defined like a problem, we made it simpler so we could do it in 3 weeks. And then we did this thing. You can see this code down here. Essentially, this is just a little snippet where I was trying to remove all the missing values, the unknown values from certain columns. And all of these like variables you can see, for example, age group, sex, symptom status, they were all defined in the data set I used from GitHub and CDC. And like they're pretty self-explanatory, but for example, it just means like symptom status means do they have COVID right now at this moment, or have they had it before, and things like that. And then when I actually applied another code, I realized that for some of the variables, like for example here, case onset interval, some variables had, and this percentage like 59%, means that there was like 59% of the values were like just NaN, so they just were like not there, or they were missing, or there was something not numerical about them. And for my data, I need numerical data. And so that was bad. So we decided to drop a certain column. So I dropped all of these columns you can see here. And the reason for that was just I chose to drop columns that either had a lot of missing values, um, or like I chose to keep certain column even if they had missing values, if in the case that they had a lot of data for those columns, because removing those would result in me removing too many of my data points. So in the end, I ended up with 95% of the data that I had originally started with. So I had quite a bit left, and then some of them were just unknown values, and I had to, just like put in zeros or things like that. Um, a big step was this, like deciding which rows to keep. So the ones that ended up staying were the age group, which is like how old they were, the sex, so female, male, and then exposure was have they had COVID before? Symptom status is do they have it right now? County was like where they live, within the state of New York, because the data sets was all for only the state of New York, and then the month that they had COVID in. And another step, also part of data science, like this is even before we got to the model, which this was definitely took the longest. So one thing was one-hot encoding, which is like a technique used to essentially line up labels and into these numerical values. So you can see here, for example, if I had like sunny, rain, and wind, it could go into a data table where um if the category for a certain like variable is sunny, then I would put it as one, and then the rest would go zeros, and as follows, as you can see here. So I applied that to like all the rows here, but I also, you can see their decimals, because we just took the average so that we can have percentages rather than just like zeros and ones. And one important thing to note is that since there was, as I said earlier, like over 200,000 data points, we had, what we did is we combined per month. So when we were merging the data sets that we were using, we combine everything per month. So for example, month one means January. So like this row up here of one, it contains like for a certain county, for example, like Bronx, New York, and it contains everything for January. And so that's the percentage, and then these percentages are like, for example, in Bronx in January of 2021, which is the year of our data set, there is like 25%, which are 0 through 17, 39%, which are 18 to 49, and so on. So I applied that to all the rows. And what this helps with is actually the linear regressor. So, oh yeah, so this is a linear regressor. So the reason I implemented one-hot encoding was because that allows me to like be able to easily see like the numerical values and the model as well, because a lot of the values before, like instead of numbers, it was just like a yes, or it was uh just like female, so it was like words, and so I kind of matched up the words with their numbers. So then for the actual model, this actually was one of the very like shortest steps, which was very surprising. Like we did it in one meeting. And I think the reason for that is probably because a lot of these models are created already. So all we had to do was kind of implement the code and then just tweak it a little bit. So with linear regression, it's like the most simplest form of AI is where it's just taking a bunch of data points and lining them up on a line of regression. So as you can see right here, like it finds the line of best fit. And this is a type of supervised machine learning technique where we already know what the output we want is. So like we already know that all the outputs are going to be either positive or negative COVID-19, and we like know the values, so we're training and testing on those values. And so this regression problems tend to have numeric target variables. So like a numeric answer. For example, if I was to actually use this model, it would actually tell me the exact prevalence rate based on the line of best fit, which would be like a formula that the model uses. So we defaulted to just an 80-20 split of training and testing data because that is what's commonly used. And the accuracy was only 32.3%, which is not very accurate. That showed us it's pretty random. So we thought, how can we make this better? There's definitely a lot of like tactics out there, but we used a pretty simple one for now. And we decided to just go with a for loop. So I made a for loop where I went from testing data from 10 to 30, which was basically like taking like, for example, 10% of the data will be a training set, or 11% will be a training data, and so forth up until 30%. And I just tested what is the optimal accuracy I can get by in that for loop. And I found that the optimal accuracy happened for when there was 23% training data, testing data. And so that optimal accuracy was 35.1%. So not very accurate, but these are the like evaluation metrics I had for this, which are used in linear regression. It was pretty cool to learn about those. And another thing I had to do was set a parameter random state equals 10. I had to put it inside of the linear regression model because something that was happening was my optimal accuracy was changing every time I ran it, even like without changing the code. And that was due to like since it randomly picks the testing and training data, I wanted to prevent fluctuation by just having the same testing training data while I was like tweaking my algorithm. So obviously, linear regression was not very accurate. So I decided to move on to random forest. This is the second machine learning model I tried. The random forest classifier, it does not have numerical data in the end. It actually just has like a classification. So for example, I have heard of random forest being used in like, detecting a wildfire and like determining if yes or no, like, is this a wildfire? Is this a not wildfire? And so in this case, it was used just to see like what quartile of prevalence did it fall into. So what by quartile, I mean that we split the P, which was the prevalence. Again, that means how common COVID is, into four quartiles from Q1 to Q4. And we just had like there was a code that did that, and I used QtCut in which is like a NumPy command to see what the quartiles were, and they were like, as you can see, the prevalence rates in my data set were actually very low, which might be due to and this is a potential problem to fix in the future. It might be due to like the data set not having all the values, since the people that reported were just self-reporting, and then like the population was just every person. So this might not have like every single value of COVID in the county. So the like rates were pretty low, but these are the quartiles I had, was from like all these percentages all the way up to 5% max. And these are basically like, you can think like the 25%, 50%, and like 75 range, kind of like maybe if you're doing testing scores, things like that. And then I also did that for the other variables, for example, like population density, sex, every column I had, I just did quartiles for it. And then the random forest will use all of these quartiles to predict the specific quartile for P, not the specific like value. It won't output a percentage, but it'll output a specific quartile, which is actually fine because in general, you just want to know, um, need to know the exact percentage. So a random forest, it's really what the name is. It's kind of a set of decision trees. So decision trees are what's used in AI and machine learning, and it's where basically the model will keep on doing like binary yes or no questions to try to get down to the answer for a specific decision tree. And a random forest is a set of decision trees, hence being the name forest. And so then it votes and kind of averages and makes the final prediction. So one problem that I was getting, and at first I did not think this was a problem, but I was getting 99.5% accuracy. And when I asked my mentor, she said, that doesn't seem right. It's kind of very big. And so we realized that it was overfitting. So overfitting is kind of, as you can see in this graph, it's when the model performs really well in the training data, but then in the testing data, it like doesn't perform as well, but the accuracy will show as good, because in when it was like training, it was like really good. And I think one issue at first of all was that I had been testing it on what I was training it on, so I had to tweak that code. And another issue was that the county variable was being implemented twice, because before I had started random forest, I had merged it with a data set on the county, and then I had two county columns. And so it was just really just saying like, oh, if it's this county, this is the quartile it falls in. So it wasn't really thinking, it was just using county. So I had to drop that variable, and then it worked with a 74.5% accuracy, so that's much higher. And I did not implement the for loop this time because I was happy with this accuracy. But one thing I had to like tweak was the n estimators parameter, and this is what's called hyperparameterization tuning, which is when there's like certain things in your model that you can change a little bit, and it might tweak the accuracy, but it can also change the runtime. So n estimators is the number of decision trees the model will use. I changed it to 100 because I was just playing around with it, and I noticed it was bigger for 100 than it was for like 50 or 20, for example. And that is true. Like as you increase the number of decision trees, you will get more accuracy. However, it also takes longer to run. So I just found like the sweet spot for me. I just wanted to let it run not too slow, but not too fast. So then I just put it at 100 and I got this accuracy. And then I also learned, which I actually did not know before, was that there are ways to like have the performation like metrics, just how there was in linear regression. Um, there's ways to see the accuracy, which is called a confusion matrix. And so originally my confusion matrix is right here. It was in just in Google Colab where I was coding. I just printed it out. And all those so the rows and the columns is all the quartile ranges for prevalence. So this side, the vertical side is like what it actually is, like the true label, and then the other side at the top is the predicted label. And so the green boxes are where it's like correct, and like so that is, for example, it's in Q1 and it's supposed to be in Q1. And then like you can see, like for example right here, this 181 is like it was Q2 but it was marked as Q1. So those are like either false negatives or false positives with the model. And so you can see I made a confusion matrix, like just a visual representation, which I really liked seeing. And you can see it was very accurate for quartile 4, like 94%, right, for quartile 4. So that's very good to know. And then for certain other things, it was not as accurate. So we can kind of see a visual representation of that. Okay, so that was all for the models. And then I moved on to the principal component analysis, which was essentially seeing what factors affected my model the most. And you don't actually include this with the model. You just basically use a data set, but I use the same data set that I had like merged and done everything for random forest with, since that was more accurate. And so for principal component analysis, what it means is that a principal component is taking certain features of your data and like kind of grouping them together. Like for example, sex and age group might be grouped together as like one PC, principal component, meaning it affects this certain part of the data set. And each principal component will have different amount of variances. And the more the variance, the more it impacts the data set. So I just reduced, it's basically a dimensionality reduction. So like if you have like 10 different variables, like 10 dimensions, you can reduce it down to like 2 dimensions. And most of the time it's used to just kind of speed up your model or speed up your process of making the model by just having like 2 things in your machine learning model instead of like 10 different variables. However, I just use it to analyze what 2 variables affect the most. So I reduced from like all the features I had down to 2 features. So PC1 and PC2, which was a 2-dimensional data set, as you can see right here. And if it's 3D, it'll just be like that with kind of 3 axes. So for me, since I was just trying to do this to explore demographic data, I wanted to make sure I get rid of like any scaling and normalization, which my mentor helped me with, and just like making sure all the data is like clean and ready for a 2-dimensional data set. And then we plotted what's called a scree plot. And now since this was 2D, there wasn't really much to plot. It's just kind of seeing the points. But you can see on the first principal component, it had more variance at like 0.19, and then the second principal component had like 0.17 or 0.18 variance. So you can kind of plot that. And in general, when you plot a full scree plot, it's supposed to be like an elbow shape. And where it hits the elbow is where you should take all your variables, and those are impact your model the most. But in this case, it's just a linear thing. So we were just seeing which one has more. So you can see PC1 has more variance, meaning it impacts the model more. And so in this graph right here, this is for the whole entire state of New York, so my whole entire data set. PC1 is the x-axis and PC2 is the y-axis. This is called a biplot visualization, where I just graphed all the loading vectors onto the like the graph. And then there was a website which we just read, and it said like there's 3 different factors you can see to like kind of see what this graph means and analyze your data. So there was orientation and size and angle. So I can just talk through with the actual graph though. So at PC1 was the x-axis, and you can see that population density and county have a very small angle between PC1. So it means they're very close to PC1. And that means that they impact PC1 the most. And then but like they're parallel of each other, so they don't really have much correlation. So I kind of did that, and in my research paper I outlined that. And then I also did a PC comparison of two different counties. I just chose Wayne and Columbia, just randomly chose two counties that were in my data set and kind of explored the comparisons between the two. The results that I got was not actually like anything completely new. It was just as expected that the exposure you have to COVID in the county impact the model on PC1, which had the most variance. And then sometimes though, sex, so female male, did have an impact on PC2, not for all counties, but for some of them. So that was interesting to see. So that is something to note. And maybe there has been work done on it, and that would be really interesting to see like how why sex impacts COVID-19. Um, but mainly the kind of impact and implications of my work was just learning PCA to analyze this, and a similar method can maybe be used to analyze equity or diversity in like future projects. Some improvements or is it using more data and more machine learning techniques, but mainly going back to the thing I really want to try is pool testing that I mentioned earlier. And maybe there's a way to implement this model that I've learned, these tactics, into pool testing. So that's kind of something I was thinking about. Um, and so yeah, that's all for my presentation. So I want to give a thank you to like my mentor. She was so helpful the whole way, and I really enjoyed meeting with her. I feel like I had a woman role model throughout the whole thing, which was really nice. And then yeah, Talaria was such a great experience. Thank you.